Okay, so today's section is it's a BOF, and the topic is CXL. And we're going to go through a few things. It's a fairly complicated topic, and it's a fairly new topic. So we're going to try and stay high level, but that might be a lost attempt as well. So first, before we start talking, how many people here know how to spell CXL? Come on, that was an easy test. All right. How many people are really interested in CXL? Is this a thing that you've come across and you've had to worry about, and it's a thing that's top of mind? Okay, that's good. That's almost 10% of the audience. So we'll have an easy time today. Okay. So without further ado, let's just keep going. So the topic, as the headline says, is what is CXL and why should networking people care? So let's first get an understanding of what it is that CXL is trying to solve, right? So in the Wayback Machine, if you've been around for 20, 25 years, computer systems used to be these disaggregated things with NUMA fabrics that were going across kilometers of space, and everything was reachable by everybody else. In the last couple of decades, the CSP model of a two-socket system with locally attached I/O became the dominant answer. And CXL is an attempt to sort of look for a hybrid way out of that. Specifically, if you look at the design on the left, which is what people are doing today, you have CPUs that can talk to an accelerator using uncached memory, load stores, MMIO, etc. You have NICs that can talk to accelerators using peer-to-peer direct, or what is commonly referred to as GPU direct. You can have CPUs that can talk through accelerators into that uncached memory, and so on and so forth. What CXL is trying to do, and we'll talk about this in great detail in the next few slides, is to address those three patterns of communication. They want the CPUs to be able to do write back, effectively make accelerator memory coherent. They want NICs to be able to do peer-to-peer direct with coherency if required, or without coherency, or something that has been called UIO, or is being shaped into UIO at this point. And you can do effectively, again, coherent and non-coherent load store as an explicit communication mechanism between different devices. Now, why do you care and what are the use patterns is what we're going to look into next. So I call that the three horsemen of CXL. So CXL is defined as three different communication types. The first one, called CXL IO, if you look at this picture, and I'm sorry for jumping around on the pictures as well, I should state that all these pictures come from the CXL Consortium website. So if they don't look good or they're confusing, blame them. If they're clear and it's obvious, thanks. So if you take an accelerator and you take a host processor, this is sort of the communication model, right? You have your CPU cores, you have your IO devices, as we've all learned, the uncore infrastructure that's not the core. And you have, in today's world, you would have PCI logic. These PCI logic bits would then talk over the PHY to a device on the other side, and it would go and do whatever it needed to do. What CXL introduces, well, actually, we'll talk about what it introduces. The first thing it did is, it said, like PCI, we have a thing called CXL IO. It's just effectively PCI, but it allows you to do two things. It allows you to reorder or go past transactions at 64-byte granularity, and it allows you to create this thing called FLIT routing, which we won't get into today. But for all intents and purposes, CXL IO is PCI baseline. The next thing it did is it said, I will introduce this thing called CXL cache. And what a CXL cache allows me to do is to effectively tap into the coherence logic of a core. So if a core was going to have coherency communication with somebody else, and typically, or I shouldn't say typically, many CPUs have an explicit coherency management unit. And this is the thing that makes sure that if somebody else gets a cache update, it gets its own line invalidated, it requests a new copy if it needs that value, and so on and so forth, and keeps the multiple CPU cores coherent and in sync with each other. And what CXL cache allows you to do is to tap into that and have external accelerator devices that can now be part of that caching domain. Specifically, and to make that very concrete, where a NIC, for example, if I was talking to a CPU, I would have to use DDIO or something like that to push a line of data into your CPU's cache. Here, what I can do is I can say, I just have a new value of that cache line. Come get it from me when you need it. We can argue whether that's better or worse, but that does make the overall system much simpler. And then the last one is CXL memory, and CXL memory allows you to pretend that you are a piece of the memory map that belongs to that CPU. So you can now imagine that I have a server in which the server sees 2 terabytes of memory, but the first 256 gigabytes is local. Everything else is actually across a PCI bus. If you ask that server, and if you ask its MMU, how much memory does it have, the answer is 2 terabytes of physical memory. But it's just distributed over a wider surface. So I raced ahead, sorry. So you have the 3 pieces, the CXL IO piece, the CXL cache piece, and the CXL memory piece. And the use cases are also sort of similarly laid out. But there is an orthogonal concept in CXL because, otherwise, so far, is it making sense? Good, because the CXL spec tries to fix that problem. So now it creates an orthogonal concept of a device type, because rather than just saying that there are 3 types of transactions, they said the goal is to try to optimize for 3 types of usages as well. And it is an orthogonal statement. A type 1 device is basically a device that does IO and cache. A perfect example of this would be a NIC. And let's say you have a NIC that was offloading some transport. Now you can say that the transport control logic, the TCB, if you will, is something that is living in CXL cache. Because now the CPU, whenever it touches a block or it says, I'm going to do something, updates it. But the NIC is capable of just asking for the updated copy rather than it having to be pushed into the NIC per packet or per transaction or per session operation. And IO, obviously, you need IO because that's the baseline DMA operation that you need to be able to emulate the standard behavior. A type 2 device is an accelerator with local memory. This would be an example. If you continue with the NIC, it would be an example where the NIC's buffers are actually in its own memory space. It's not actually DMAing out of host memory, but it's DMAing out of local memory. And maybe it's doing that because it is constructing NVMe over TCP or some other transport like that, where it has to do some assembly of its own. And for that assembly, it has fragments of memory that it has complete control over. Now, why would you expose that to the host? So that the host could actually manage that. It could say, here's all your NVMe headers that you need to use, or here's your TCP headers that you need to use. And when I give you the underlying, you should put them together and send it out. Such a device would have CXL IO, cache, and memory exported out of the device. And these are all capabilities that the device exports, just like PCI. And to keep it really confusing, there's a type 3 device, which actually is a reduction in capability, because this one just has IO and mem. And I'm saying this a bit facetiously, but I have never understood the logic here, because it seems like there is no progression I can map back to what a type 1, 2, and 3 should actually be. But I do think it's actually the order in which these devices were imagined to be used. So a type 3 device has only memory and IO, and it would be something that looks like specifically just a buffer or expanded memory or a way for a CPU to have a bigger physical memory level than it otherwise had. I'll pause here for a second to see if so far people are mostly following along, and if there are questions. Yes, was there a question? Okay. All right. Okay. So let's talk about what does that mean, right? And this is a very important thing, right? Because what has happened in the context of CXL is that people have started thinking about capacity as the only thing that matters, or capability as the only thing that matters. But it turns out performance is never that simple. There's always a question of, in the hot path, what are you doing? So a position that we have in Fabrica, that I should have started with that as an introduction. I work at Fabrica, and so on and so forth. A position that we have is that memory is a hierarchical problem, that you need to think about memory in a strict hierarchy, and you have to understand the trade-offs. One very interesting thing, for example, in this graph that should jump out at you is that today with 800 gig networking, you are actually running at higher bandwidth than actually a channel pair of DDR5. I'll let that sink in for a second. Your network can swamp your system. Your CPUs can be starved because your network is just doing what it was doing normally. And that's a very interesting inversion of state, right? Like people have not really digested that completely, in my opinion. And it's true because today most NICs, most host interfaces do not run at 800 gig capability. And 800 gigabits, as in 100 gigabytes, is a very, very large number. But if you have to think about CXL and if you have to think about I/O, these things have to be considered together. In fact, this is why I made the point yesterday in Jesse's talk that if you think about schedulers and I/O costs, and you think about it purely in the context of high-speed networking, you're going to actually end up avoiding or ignoring this thing that is lurking in the shadows, because the whole point of the CXL ecosystem is that I can build now a hierarchical communication model where up to a certain distance and up to a certain radix, my networking can just run on top of a CXL link because I don't need anything more. Anyway, so and the important part again in this table also is the rightmost column, because if you look at the rightmost column, people have thought about memory as something that's always a memory dereference. But it turns out that if you really think about the entire continuum, there is a continuum. There is a point at which you switch from a pure pointer dereference to a swap-based copy. And where CXL is really interesting is that L3 section where it can actually operate in both domains at the same time. And that is the game changer in my opinion. So, but CXL is relentless, so they will continue to add features and thus confusions. So today's, and PJ will talk a lot more about it later in the session. Today's devices are typically a CXL 1.1 plus asterisk type device, and every PJ is laughing because every vendor defines the plus and asterisk a little differently. But the goal most people have been striving towards is a standardization around CXL 2.0, and CXL 3.0, and in fact already 3.1 is sort of the ultimate target that everybody is aiming for. And why is that so? So CXL 2.0 adds in this notion of being able to create memory pools and to create these wide switched layers as shown in the picture on the left-hand side. And what this allows us to do is it allows us to plug in type 1 or 2 devices as individuals, but more importantly, that group of type 3s that can be presented to a group of hosts across some limited boundaries. There are some limitations about how you present them. The terms SLD and MLD stands for single logical device and multiple logical device, just like think of it as SRIOV for memory. And it also adds a very important context of integrity and data encryption, which allows you to create the foundation for what is being termed as confidential computing going forward. But 3.0 is the big jump. In 3.0, the idea is that you can now have a multi-headed coherency domain. You could have multiple computers that share multiple resources or that share pieces of a resource in a coherent way. And every one of these devices, when you touch it, you can get a coherency back invalidate, and everybody will sync up. This sounds great in theory. In practice, is going to be a very interesting conversation because you're now going to have a trade-off on coherency traffic overhead versus efficiency of communication, because that bus is still getting used. So we'll see where that goes, but that 3.0 is sort of the ultimate dream that most of the people in the CXL community would say they are sort of driving towards. And it adds this notion of multi-level switching. It allows the notion of very fine-grained partitioning. It has, like I said, some enhanced coherency capabilities and so on and so forth. So we'll see when 3.0 comes out. The current target is 25, 26 timeframe is what I've been told. Yeah. Generous. That's generous. Okay, we'll see. Okay, the last, I think this is pretty much the last thing in CXL I want to talk about. So the one other thing you have to understand about CXL is that it's fundamentally an incoherent, or it's fundamentally an asymmetric protocol. And this was by design. It's not accidental, right? So the whole problem here is when you build tightly coupled systems, as many of us have learned as part of building large network distributed systems, tightly coupled systems tend to fail very, very dramatically. And CXL was built to not be a symmetric tightly coupled system. The whole point is that every side can decide whether it wants to initiate a conversation, and at that point it becomes asymmetric. And what the picture is trying to show is exactly that, right? Like, you're not saying that every time the accelerator on the left does something, the CPU on the right has to be notified, and vice versa. The asymmetric model allows the picture on the right, in this case the CPU, to say specifically and what CXL transaction it wants to signal to the accelerator, and it can keep that. It makes decisions on which of these signals it wants to send to whom. And it also actually allows you to make deadlock prevention a little bit easier because you don't have circular dependencies out of this design. But what that actually means to an end user is this. It brings bias as a good thing. For all the people who've had lots of training to the contrary, what this allows you to do is to say a piece of memory or a resource can have a bias towards the device or a bias towards the host. Because when I say that you and I are going to be completely in sync with each other, somebody has to have authoritative sort of rights to break a deadlock. And this is what the bias actually tells you. So you can now say that I can either present, let's say memory can be presented as biased towards the device, in which case the primary copy lives with the device and only a shadow or a synchronizing event is sent to the host, or vice versa. And actually in memory, that's probably a bad example, because for memory, there's an explicit notion of the home node, and the home owns all of the memory that is associated with it. But every transaction in itself has a notion of a bias, and that's what enables the asymmetry in the system. So I'm going to switch tracks for a little bit and talk about how and why, and Fabrica is here talking about CXL and why we care. Because we think that CXL as a fabric is very interesting, but it is also an incomplete story. And we believe that the real intersection point is when networking and memory actually merge. Because at the end of the day, right, like while everybody here, I think everybody here, who is very deeply involved in networking thinks about moving packets and bytes from one place to another, the primary goal has always been to move memory. It's always been about memory, right? It's just that we forget about it sometimes. So if you think about memory as your problem, and if you think about the fact that networks are now capable of moving memory faster than memory buses, you get to rethink how your data center looks. And what we are building, for example, is a switch that looks like a CXL switch on one side, but it has integrated into it the ability to move data, to be able to create memory pointers, and to be able to move it over the network using standard IP, Ethernet IP type transports over to destinations that are farther and therefore incoherent relative to the CXL infrastructure. Now, if you build a system like this, what problems can you solve that you couldn't solve earlier? So I'm assuming a lot of people here know what Redis is, or Redis is. I might be getting the pronunciation wrong. But fundamentally, it's a hashed mechanism of taking a client and connecting it to a tuple of compute and memory, right? So that's what this picture is roughly trying to say, that you have nodes, which are servers, within which you have shards. Shards are a certain amount of thread capacity and memory, and you hash into those shards across those nodes, and that's where your table lookup goes. Now, if I was to say that I can reconstitute that unit, that compute and memory block, I can rebuild the world this way. I can say that all my memory lives in CXL, hanging off of an array of switches. All my compute is just directly attached to those switches. And what I get is configurable nodes, configurable shards, and the entire data center as my memory capacity. How many people have had a conversation about my in-memory Redis database is not fitting in my memory? No one. Okay. One. All right. Thank you. That was a pity. Two. I got two. Okay. It's a reasonably common problem if you are running Redis in production systems, and this could completely alleviate that problem. Another example would be memcached, right? So if you think about memcached, what does memcached do? It basically says that I have a bunch of caching servers that take storage that is replicated and sharded and then present them through front-end web servers. I could completely redesign that system. Ooh, that's an interesting PowerPoint artifact. I could completely redesign the system to say that on my CXL switches, I take my storage and I move them across the network. I can still replicate and do what I need to do, but I can now present memory hierarchically such that the cache access that's coming from the front end is always serviced, because I can get the right pages into the right CPU's accessible memory on a backend network. It's in solutions like this that you can say that I can actually now take advantage of the fact that memory is disaggregated, reachable in a zero copy kind of way over a very high speed network, and effectively rebuild data centers to look completely and radically different from what they look like today and have a dramatic improvement in efficiency. The last example I'm going to talk about is inference, because as I don't know if you guys got this memo, but you can't finish a talk these days without saying AI in it. The last talk, or the last session, already covered everything in AI and ML, but I'm going to try to squeeze something in. So if you think about inference as a problem, right? Cost of compute is a very big problem. And if you think about that fundamentally, one of the things that you have to do is get user context to the right GPU in time, because people are reusing GPUs or ML accelerators. Maybe it's not a GPU. And one of the big problems then is, where do you store the context when you swap somebody out? And it turns out this is actually identical to the previous slide. If you have a memory store that is fast, close by, and you can swap out to this memory store and have a very wide radix of GPUs on which you can land workloads, and then quickly refill the context into that GPU, then you can reduce the number of GPUs you need to hit a particular SLA. And that's really what this slide is saying, that if you do the naive allocation, you're under heavy load, queuing delays start looking pretty bad. Whereas if you can move the data out and build a stateless model of allocating a GPU on the fly, then you can flatten the curve out and you violate your SLA under a much heavier load ratio than you would otherwise. I think that's all I had. What's going on here? Okay, that may be the signal that the slides have ended. Okay, so that's all I had. I'm going to switch over to Alejandro, who's going to talk about in greater detail about a very innovative use case he has for CXL, and we will take questions after Alejandro is done, if that's okay. If you can wait, if you can't wait, we'll take it right now. You can wait. Okay, let's do that then. And you'll see why we need to do that. So arrow next will.
Okay, so now that it's pretty clear what it's CXL and how can they be used, I'm going to give you a potential use case. So I'm afraid I can't compete with other slide designs that we have seen today. This is the more complex one I have, and it's all, the credit is all for my little daughter. That she told me, you cannot have a plain white background, Daddy. So, okay, that is all. What she doesn't know is I just have used it for the first slide. So I need to start also saying, disclaimer, I work for AMD, but I'm not representing AMD here. I'm not representing any AMD's view, any AMD roadmap. So I just want to share an idea that I I have for using CXL for solving a problem that we have nowadays with semantics. So this is the agenda. I'm going to explain which semantics I'm referring to, which functionalities I'm referring to. I will start with a brief introduction explaining why I'm talking about this, because it's not, for me, CXL is not something that I was looking a problem to apply, but it came to me for something that was I was working and really didn't understand how it could work. So I will then explain how CXL, how these semantics can be used or are being used with the Linux kernel, with the Linux OBS TC. I will introduce the concepts of slow path and fast path. Some people here, I guess, are familiar with, other probably not so much. So I'm going to slightly change this terminology. I hope it's not confusing, but I think is required for understanding what we are talking when we are referring to this slow path and fast paths. And once, well, I will introduce the Linux TC used for this semantic functionality solution to have the offload. And I will describe the problems that we have now. So hopefully once I have done that, I will be ready for presenting how CXL can help there. Okay. If I have time, I will also talk about other possibilities, because as Sujit has commented, with CXL, you can have this kind of orthogonal design. You can have interface really easy to do between the host and the NIC. So other things that are complicated because you need extra channels for doing that kind of stuff, well, you just need to have maybe a different memory address for doing it. And yes, some takeaways for the end. So my first introduction to CXL was probably around 2018, something like that. And it was, initially I thought it was mainly for GPUs. That was, at that time, I was the reason behind CXL. Sujit has commented that the main reason initially was for CPUs, and then GPUs are another kind of potential sharing between the high-performance devices and the CPUs came later. Anyway, by the way, I knew first about other protocols or implementations like CCIX. In 2018, I think it was ahead of CXL. So it was a surprise when I came back to study further CXL. Well, this idea that CXL was then ahead. And I think it's not ahead, it's just mainstream now, and the other ones are. ARM is doing, I think it's working with a solution, but anyway. So it's also important to say that this kind of sharing has been happening with PCI devices. So you can write, you can read from the CPU to this memory, but the point is with CXL that is going to be optimized. The latency is going to be better, and you have this coherency that is going to be really important for, I guess, a lot of the scenarios. So. Interestingly, at that time also, there was another discussion, and it was about bringing the NIC closer to the CPU. And it was literal. With CXL, we can say is the connectivity that is going to put this closeness between the two. But at that time, the idea was, okay, let's see what we can do if we put the NIC inside the CPU chip. Something similar that was proposed for memory controllers. So I remember working for then another company, and talking with the main hardware architect there. And he got one of those machines prototypes for this. And at one point, I was thinking, okay, how can we improve the VM-to-VM intranode communication with the SmartNIC? Because if you think about it, if you have the VMs talking straight to the hardware, it's a waste of time, waste of energy to just send the packet to the hardware, to the PCI, then the packet back to the host. So for that, there are some solutions, backend software solutions for doing this memory mapping in the host that is far better. Of course, if the CPU cycles can be available for that. So I was just thinking about how can we solve that. So I thought, okay, what if we can put some hint in the TX descriptor? Then the hardware just get the descriptor and it will know that the packet is for another VM. And then magically, the NIC is going to swap things around, mapping things instead for one VM to another one, right? And then this hardware, this brilliant guy, he started to shouting, yes, yes, this is what we need, Cherry. I guess some of you know about Cherry. Cherry is a protocol for improving security, and the idea is to have finer granularity for memory mapping. So in this case, of course, if you want to do this swapping in the memory, in the host, you need this kind of things, plus the capability in the NIC for doing it, right? So this is not relevant for the talk, okay? But I think it's important because if you think about CXL and NICs and networking, the most natural way of thinking is the data path. How can we send packets faster? How can we lower the latency, right? So my talk is not about that. My talk is about the control path, okay? So I have worked in two different companies, two different SmartNIC projects, and both having OBS offload, OBS TC, using the Linux kernel TC functionality for the offload, and well, plus contract, okay? So since it was established that this was the way for doing hardware offload with the SmartNICs, it has not evolved too much, right? And the question is, does it need to? Is doing what is required? Okay, so my statement here is that we cannot rely on this TC for doing massive virtualization. Mainly because I think there was a misconception there that it doesn't take into account the rate of change of the things that need to be offloaded. Okay, so if you put that into the picture, TC is far from optimal. And I'm talking, so my main interest is about the offload, okay? But if you are familiar, I will introduce that concept of slow path and fast path. If you are familiar with that, the slow path means the packet handling, the matching and action is going to happen in the CPUs in this slow path, and is going to be is going to play an important role in the whole solution. If you stress out the slow path, is going to be bad because you are going to have more problems for offloading things. The misconception is it was thought, okay, this is just for hardware offload because it's going to be in the NIC. We don't care about the TC slow path. We don't care about all this, the limitations that I will describe later, okay? I think that is a huge misconception. So if you think about it, it's impossible that this solution can work, okay? There are some vendors saying, yeah, we have clients using it. Well, probably, but are they happy? Because it requires a lot of CPU cycles, right? And the offload, because the offload has also problems. This latency putting the rules and the flow states in the hardware. The higher the latency, the more packets are going through the slow path, because the hardware will know, we don't know, we will not how to handle them, right? So at the end, if you think about massive virtualization, having dozens of virtual machines, and each one requiring a high number of rules for matching and actions, a high number of contract states, it's impossible that can help, right? Okay, so now let's talk about the smart NIC that I'm referring to. We have a lot of possibilities for offloading things to the hardware, and I think probably the initial idea of these smart NICs was to accelerate networking for virtualization for VMs, and then you have VMs talking straight to the NIC. You don't want to have the device emulated and with a backend in the host using CPU cycles, because you want to put those cycles to the client that is paying for the VM. So you have SROV, you have virtual functions, so you give chunks of the NIC to those VMs. You have IOMU for ensuring that from inside the VM you can program DMAs and not putting in risk other VMs or the host. You can have things like BDPA, virtual I/O through hardware offload. So in these NICs, all the packets that come from the VM or packets coming from the wire are going to be handled by the NIC following those match and action tables, where the packet will be matched against these rules. If it matches one of them, there are some actions that will be applied. For example, for the redirecting a packet to a specific VM based on the channel and something probably maybe in the header, in the inner header, then you do the encapsulation, send the packet straight to the VM, right? This is what is the fast path. And this is where the terminology start to maybe to change a bit, because this idea of fast path and the slow path is when the packet doesn't have a match, so you don't have, the NIC doesn't know what to do with the packet will go to the host, okay? And if the packet goes to the host, that is the slow path. Then you have their OVS for dealing with the packet, okay? So originally, this was an OVS thing. And the idea is that the fast path was the kernel data path. The slow path was the user space. Okay, so this is related to how OVS works. So in this case, I'm slightly changing the terminology. So we have the fast path is the hardware. The slow path is the kernel. The user space, if it needs to come, is the slow path, right? I can also have the fast path and fast path in hardware, depending on how you are going to be able to use these maths. And so the way of implementing these maths and action tables in hardware is through CAMs, BCAMs, TCAMs, okay? Because you can match a lot of rules in parallel. And in one cycle, you can have the answer, the actions to apply to that packet, instead of going sequentially or using hashes. The problem with this hardware implementation is they are really demanding, consume a lot of energy, they are expensive, and at the end, the size of these maths, they have a limit. So the solution is, for the massive virtualization scenario, that is not enough. So the solution is to put a DRAM inside the NIC, okay? So you have the fast path, that is when the packet can be handled with the data inside the match and action tables. And you have the fast path that then you need to go to this DRAM, or maybe you have a cache between the two things, okay? So I'm not interested in this square because this is the switching, the logic. This is the secret sauce that every vendor implemented in a specific way. I'm not going to talk about that. This is also where P4 supposedly can help for implementing this pipeline of matching action tables. What I'm interested in this communication and how these tables and this DRAM is going to be populated. Okay, that is what I'm interested in and what this talk is about. Of course, this is a really simplistic view of the SmartNIC. It's just functional way because you don't have this kind of channels to the VMs. It's all go through the PCI, but it's just a logical picture. So, okay, so now that I hope it's clear the kind of SmartNIC I'm referring to, let's talk about how the Linux kernel use these SmartNICs. Because the idea is to have the SmartNIC doing the packet handling, okay? So I'm going to make here an assumption, and is that the slow path, fast path scenario, where the fast path is in the hardware and the slow path is in the host, makes sense, okay? It means that the packet can be handled by any of the two sides, and it makes sense because, well, first of all, you have two ways of populating these matching action tables or the DRAM. Is a proactive way, you will put everything then when the VM is deployed, or you can populate that when something happens with the traffic regarding that VM, right? You can say, well, I don't believe in this kind of split scenario. It cannot be handled properly. But this exists because of a reason, right? This reactive population exists because of a reason. You don't want to waste resources in the hardware until they really are needed, right? So it makes sense. Probably there are some solutions for specific hardware, no hardware clients where you can do the proactive thing and it works. But if you're a cloud provider and you need to give this kind of solution, you can't rely on just the proactive thing, right? And the problem is the rate of change. How those rules for matching an action are being installed do matter, okay? Because it's it's more demanding than what was expected, or I would say, yeah. I think the misconception is, okay, maybe we knew that, but you know, it's going to be in the hardware. So if this is not optimized, it doesn't matter. It's going to be in the hardware. Yes, right, that's right. But we need to put all the control path data in the NIC. And if you have this kind of reactive solution, you need to do that really, really quickly. If not, you have latencies. And a latency doing the offload means that the slow path is going to be used once you theoretically install the rule, okay, until the hardware can use that control data. All the new packets of that flow, the NIC doesn't know yet how to handle them. It will go again through the slow path. So you have more CPU cycles in the host, right? And then other reasons for this, the slow path. One is, of course, the hardware has limitations. Even if you have a DRAM, maybe you want to have more rules or more connection states, flow states. So it's a good idea. Then you can also support things that the hardware doesn't support, right? And the last one is nowadays for the connection tracking, that requires the slow path. Because the hardware right now, if it goes with the Linux TC offload, it is not going to handle the control the contract state changes. That is going to be done by the kernel. So the packet needs to go to the slow path first. The kernel will establish the connection, and then the connection will be offload. Then the hardware, the fast path, can use that rule with that connection state. So the slow path matters, right? And for the slow path, you talk about the kernel, you have the OBS-TC, or just for the sake of this presentation, there are other options. I think there are some cases where you can use ePPF for containers, things like this. I'm interested in the OBS-TC case, right? So I will talk about that in a sec. Well, yeah, so the slow path is through the Linux traffic control, and it is through the TDC flowover. That was an extension when it was decided that the way of doing hardware offload through the kernel was through the TC. So if there's no, the kernel doesn't know, the slow path doesn't know how to handle this packet, then it will be sent upwards to the user space that it's a slow path, and then it connects to the OpenFlow controller in other machine for knowing what to do, okay? So at the end, the system will have the information for handling that packet, that flow. So this packet and subsequent packets from the same flow, and it will be installed in the TC in the system. And if there's a NIC supporting the OBS-TC offload, it will be offload to the hardware. So, and as I said, with contract, the slow path is necessary even after the TC rule has been installed, because it requires the flow state to be established first, and that is done by the kernel. So you can have the rule in the hardware, but it will not match because the flow state doesn't match, right? So it will go through the slow path. So again, rate of change. If you think about applying rules for the matching actions, that can be demanding. How many rules do you think that a VM requires? I don't know, but we have seen a high number of them because it depends on traffic, and sometimes it depends on things like the TTL of the IP there. So the match will depend on the TTL. And so you can have an explosion of rules per VM. But with contract, it's even more demanding because assuming you have, for example, a server in a VM, you will have clients connecting. And if all that needs to go through the kernel for establishing the connection that is a specific IP source, IP destination, then needs to be offload. So it's quite demanding if you think about the rate of change that is required. So then why to use the kernel TC for the slow path? So when OBS, that is the Open Virtual Switch that I refer with the OBS-TC. So how to support the networking in virtualization. Initially, the OBS was using emulation. So the VMs were connecting to this OBS switch in the kernel, and it was all through emulation, okay? Well, you can have Virtual, or you can have TAP, other kind of devices there. But it was using CPU cycles. Then there was the opportunity for hardware vendors offering this OBS offload, where everything that is done in that switch in the kernel can be done in the hardware, right? And the point was, okay, how can we offload this OBS functionality to the hardware? And at the time, there were several solutions. Different vendors have had their own offload mechanism. There were some discussions in the kernel. there was not an agreement about how to do it. In this case, this is not the first time that happened. In other scenarios, at the end, there's a discussions, there's a convergence, and at the end, the kernel implement a generic way, and then you can have other specific vendors. A specific vendor for, sorry. I missed my point. Yeah, specific vendors for doing this slightly different. In this case, it was not that because what was proposed. We have this TC. With TC, we support match and action. Why not to use it? Okay, it just requires some slightly changes, TC flower and things like that. So does it work? Well, as I say, I doubt it works. Okay. By the way, this is not a critique against TC at all. I think TC plays a role, but it should not be used for this scenario. Okay, it requires other things, more optimized, because this kind of slow path requirement that I'm commenting. So, okay, so I'm not going to comment this. There are some jokes for the only node to remember. So what's the problem with TC? So first of all, QDisk cannot be updated in parallel. Okay, that is a huge problem if you think about the rate of change to apply new rules. And someone tried to change that in the kernel mailing list with a patch, but the answer was no, because that requires locking inside the TC. That is not allowed. It's complex, and at the end, this is just a control path. We don't need to optimize it. This is the misconception that I'm referring to. The rate of change does matter. So all the things that you have a good number of rules. The matching is going to be sequential. One rule, it doesn't match. The next rule, okay, is hardly optimal. The parsing and matching is is done per rule. Then this idea of the syntax gap. Maybe I'm the only one concerned about this, but if you think about it, with this idea of the OpenFlow OVS, you have the syntax rules in OpenFlow syntax. It will go to the OVS, that it will translate that to TC, and then those syntax will be translated to the statistics of the hardware. I don't know if I'm the only one, but it doesn't make sense out of translation there. Then the TC ossification. I think probably that it was some time ago just a hardware thing, but before in the software data path is because this kind of, we need faster ways of implementing new protocols, and we need this kind of flexibility. So, and the end is the contract. This contract it was designed for the scalability, or a better scalability. But the problem is contract with TC is attached to TC processing. Okay, so at the end, it suffers from TC, this bottlenecks that I'm commenting here. Regarding P4, the possibility of having a P4, a slow data path. Okay, I don't know if that is going to happen. I think it's more likely to happen in the software than in the hardware, because in the hardware there are some huge problems to solve. But then it has been discussed, should we use eBPF for that, for the backend, or should we use another kind of, I don't know, and I don't care. As long as the implementation solves the problem that current TC has. So really, I don't care, okay? I care about the representation, about how that data is going to be there. Because if we believe in this P4 thing where it's going to be the same thing in the hardware and the software, okay, should not then we use the same control data in one place, should not just update once and avoid a lot of problems. So I'm going to give in some hint about what I'm going to present with CXL. But then the offload, okay? I've talked about the problems with the TC processing in the software data path, the slow path. But what about offload? The offload is not working either. And I have studied that. And yes, this is the conclusion I have. This can't work for massive virtualization, or it can work, but far, far from optimal. So the TC rule, when it's updated, if the hardware supports that, that will be synchronously done after the TC rule has been updated. It means that driver code will be invoked somehow, and the driver will first check if that can be applied. It supports all the matching and actions there. Then it will translate the TC rule to the intrinsics of the hardware. Then the hardware, the rule will be sent to the hardware. Different ways to do it. To do that, you can have a specific control path channel. You can use the data path. In both cases, you need something in the hardware. For that, usually this requires some the hardware aching about this rule being installed, or the rule being installed. Usually, you have an identifier for working with that rule later, and then is the problem of okay, we have sent that to the hardware, but when is that hardware going to use that rule? Okay, the rule is in the hardware, but how is that? When is that rule going to be implemented in the maths or in the DRAM if there's no math? That's another possibility. With contract, it's the same thing. Well, it's not the same thing because it's asynchronously done. So when the contract is, the flow is established, work is created, and then a kernel worker will at some point, when? Well, we don't know. It will depend on the competition for the CPU. But at some point, that flow will be offload, invoking driver code, and the rest is similar, if not the same, that with the rules. In this case, for example, is just one work per flow, and is one work per direction per flow. So I guess that can be optimized. But the main problem is also here, when that flow can be ready for the hardware data path use it, okay? So trying to give here a graphical vision of what I have talked about. The problem that I want to emphasize is the duplication of the data. At the end, you have the data in the DRAM in the host. You have the data supposedly in the DRAM, or maybe just in the maths. It depends on how this is done by the hardware. This is up to the vendor. You can think of different scenarios there. But probably, if you do this design the dimension properly, you have a DRAM there because you are going to need it. Okay, so at the end, the data is going to be duplicated in two different DRAMs. And another thing that I want to comment is this way of okay, the data is sent to the hardware, but when this is going to be here or when it's going to be there, because you need something here, right? You need a specific hardware there for redirecting that control path data to the final destination where the hardware data path can use it. This is up to the vendor, but it requires some kind of firmware hardware design for doing that. And then you need to dimension that properly. So my point is, okay, so if you have this design where you have a DRAM, why not to put just that in the DRAM to start with? Avoid doing first this math population. Let's populate the DRAM, and then you will have this kind of solving misses in the maths, right? And if you do that, you have DRAM here and DRAM there. Okay, cannot we use the same DRAM and here is where CXL comes from. The idea of CXL for the control path comes in. Okay.
By the way, I think time maybe. Is there another talk after this? Or?
Yeah, we have one more. So,
yeah, and I have a lot of questions, so I don't know how you're going to do this.
Okay, so I will go there, straight to the CXL thing. Yeah. So my idea is to have CPU updates for the control data path in the hardware. Just to write, the CPU will just write to the DRAM. Which DRAM? A DRAM in the device. Okay, once it's there, both the CPU, slow path, and the fast path can use them, or this data, because CXL gives this coherency for the slow path. Okay. My point is, if this is going to be in DRAM, you could argue, well, you cannot force vendors to have this specific or generic way of putting the match and action rules or the flow states there. Why not? It's going to be the same thing, right? And if you have some specifics, some intrinsics to the device, and you are doing that right now in the CPU cycles in the host, why not to do that in the hardware? And then the burden is in the hardware vendor, right? So I think it could be good to have a standardization at the DRAM level. After that, you can have your intrinsics. And this is the point. You can use this data in the slow path. So you will have just one, place to update. Okay? So you are going to save resources. By the way, this is more than duplication, because I will say for all the NICs supporting this kind of stuff, the driver is also keeping data about the flows of loads and about the rules of loads. Okay? Okay, so this is what I have talked. Driver not involved, okay? Should not be cool not to have these translations and no driver at all involved in this thing. I think it's possible, but of course requires some discussion and probably someone pushing some vendor or some big client requiring this. Okay, so this is what I'm saying about the standardizing the DRAM contents. I think it requires a lot of discussions and an agreement of that. Remember, this is not about forcing what to do with the secret sauce. It's about standardizing what the DRAM is going to have, the contents there. If you want to have then your specific format, go ahead, but not put that in the burden of CPU cycles in the host. And well, this is what I think should be the solution with CXL at type 2. Probably the more interesting thing to discuss, and probably if this makes sense, is it will be research about how to access that data in the slow path efficiently, and the same data there to be used by the hardware. But I think that's doable. Nowadays, there are switches that they have this kind of DRAM with hashes, so nothing really weird about it. Okay, so this is to state that this is not exactly what Srihit, this classification that he has commented. I think this is the way. The device having DRAM and the CPU writing to DRAM, and the CPU through this coherency being able to when access that control data and use it in the slow path. Okay, so I'm going to stop here.
Yeah. Do you want to take questions now or not? Or comments?
Yeah, sure. I think Jamal has been keeping quiet very successfully for the last 15 minutes while we switch laptops.
Okay, so
but you have a 2-question max, so use them wisely.
2 questions and a comment, is that okay?
No, 2 questions or comments.
Number one, I think your nugget of your idea is when we have CXL, we can map this into the host. The tables will be written into the host, and then every vendor will conform to this scheme on the.
So, tables will be in the device.
Right. Sorry. So that's one. So I think that's a great idea. I don't know when CXL will be ready, but today that's not how we do things. We copy things. Today, at least TC keeps copies in software, and who knows, maybe some vendor keeps copies in their driver of all table entries. one thing it's a very bad idea to do this reactive model you described. And unfortunately, OVS does that, but that doesn't qualify as TC. That's OVS. Okay, the opportunity of packet reordering is humongous, and people have seen it in the field. I would never use OVS myself, but I'm biased. Number two,
no.
Can I
said no. You're not biased.
Oh, and we've never used OVS for that reason, because of the potential, not potential, but in the field, you will get packet reordering depending on how fast you can update the control plane.
But do you realize that there are people using OVS TC?
From what I've been told, there's not that many people. At least all the vendors that are deploying this, other than Red Hat, there's not that many people deploying OVS in any case. So that's one. So you could probably get vendors to agree with you on how to standardize what the DRAM, on how to write to DRAM for the tables. I think it's a great idea. But I think some of the things you're saying are conflating TC, had nothing to do with TC. Really.
So this is a CXL talk, just for the record.
Right.
So if the conversation is about formatting that memory and how that memory shows up, that would be on point, else it's offline. But we are ready to go. So let's.
I'll stop here, but we can talk offline. I just think that your idea is great. But the idea that there's a reactive model versus a proactive model, I mean, I think even your own company has a piece of hardware that can do proactive approach. Intel does, I know. The Intel P4 hardware does this.
If you can do
you don't have to do it in software at all.
I don't think proactive can be applied for every case. And that's the point of...
you can write a P4 program to do that. I mean, you may not have to look at... You can even look at ACK sequence numbers if you wanted in hardware. Anyway, in P4TC, we do support it in software. And when the vendors are ready, they can push it in hardware if they want. Anyway, I'll stop here because you're out of time.
Yeah, so we have...
we should talk.
Did you have a question?
We have one more question.
I just want to do a rhetorical question. Anytime there's discussion about a slow path, fast path split, I always get really nervous. We know time and time again, and in OVS, we've seen this. If you have a slow path, that is a liability for denial of service attack. And what if your slow path ends up being the common path, all of that good stuff. So what I didn't really get from the presentation, how does CXL help that, right? So if we could say CXL makes the slow path 20 times faster or something like that, that would be good. So I'm just saying, maybe there's something to think about because I do want to get to PJ, but just
I think the
question to ponder is what is the net effect of this? In other words, why is this a paradigm change?
You have a zero pose for doing offloads because it will be as a matter of writing memory. With this idea that they present if everything is...
So I think the precise statement is that the table can be shared. So your slow path and fast path stay more in sync with each other. That's it. That's the CXL value. It doesn't add anything else on the IO path, right? It's not doing anything magical on the IO path.
But I guess I'm missing, so if CXL is a paradigm shift, where was the shift? I mean, I understand those concepts, but maybe some expectations of how this affects performance or something would be helpful.
If you can, the latency of doing the offload be reduced to 0. The subsequent packets are not going to go through the slow path.
Right.
So then the slow path is less a burden for the system.
Yeah, but that's the fundamental premise of a slow path, fast path split, is that you want to get into the fast path. But what I'm saying is sometimes you don't get into the fast path. If you're stuck in the slow path, then we're in a world of hurt. So I'm asking, would CXL help that somehow? So my hope was we could eliminate the slow path completely. I guess
so we're going to move on. We're going to move on. The answer is no. All CXL is going to do is give you the ability to manage your fast path better, right? If the problem, there's no magic here. If the problem was memory, and you were fast path limited for table size, you may be able to do better fast path table management by moving the active context in and leaving everything in the slow path as your catcher. That's it. There is no...
It's definitely an improvement over the current approach.
Yes.
You're making multiple copies.
Okay, so we have 20 minutes. Go. We can take questions at the end.
All right. Well, I was hoping to get out of Netdev where I didn't actually have to give a talk, but Srijit kind of roped me into this and said, hey, you know something about CXL, maybe you should talk about it. So thank you for the opportunity again. And at least this time we don't have an hour delay of getting the AV going like last year. So for those of you who don't know me, I'm PJ Waskevich. There will be a test on how to pronounce that later. I'm a Linux kernel engineer, among many other things, at Jump Trading. We're a high-frequency trading firm. If you haven't heard of Jump, that's actually fairly intentional. We're pretty secretive along with a lot of the other high-frequency trading firms out there, but we are very interested in things that can reduce latency, increase bandwidth, sort of. But latency and predictable latency is really kind of our bailiwick to be very successful in the market. So Srijit and Alejandro got to talk about really cool stuff about like what is CXL and like what are all the things that it promises and how it's going to solve like world hunger and really cool ideas. And then I'm going to talk about actually like what's actually happening today and how not straightforward it is to actually get it to work. So bear with me. So CXL finally has arrived in the real world. And I will talk about some timelines as to why this is kind of a fairly significant slide. But a couple things, I'll just kind of go through this quickly because these things were already sort of covered, but I just wanted to have a base understanding of things. One misconception I think a lot of people have when I talk to them about CXL is that they think this is an extension of PCI Express. And I want to make sure that that's very clear that that is not the case. CXL does use the physical interconnects that PCI Express has. So same slot, same pin, same traces. Physically, like the I/O controller on a CPU die also has CXL in it, but it is not, from a protocol perspective, an extension of PCI Express. Things like CXL.io, like Srijit talked about, is basically PCI Express within a CXL flit. They're called flits, not TLPs now. It's kind of the brave new world. Also, CXL, and this is kind of a pet peeve of mine, so just bear with me, and then you can ignore it. CXL by itself actually isn't a protocol. It's a collection of protocols, right? So PCI Express is a protocol, right? That describes the memory reads, memory writes, the TLP formats, but it's a fairly basic protocol if you boil it down. CXL is actually 3 different protocols. CXL.io, already said it's equivalent to PCIe. CXL mem, again, we already talked about all of this, but memory coherency with the host. So my RAM that's sitting on my device, like a GPU, think about a GPU with like 16 gigabytes of GDDR or something, HBM something, it becomes part of your host memory map, right? Versus today where you have to go through like hoops and, you know, pick up your leg and memory map things different ways through some kind of private doorbell to, you know, access that memory on your GPU. This now is, it's part of your memory map, for better or worse. And then cache. And this one I'm not going to talk too much about because one, it could take a whole day to talk about this, CXL.cache, and what that actually means. How does that actually work with a CPU when you become cache coherent with the CPU, right? So just think about it for a second that today you have, you know, multi-socket CPUs or even one socket with a bunch of CPUs, a bunch of cache home agents, and they're all coherent, they all talk to each other. You touch a line, someone gets invalidated, everyone's happy, everyone has a good view of the world. That is how CPUs have lived and breathed now for quite a long time. CXL comes in and kind of like busts open the wall down like the Kool-Aid man and says, I want to also be part of the cache coherency protocol. It really opens up a lot of interesting use cases. Like Srijit was talking about, like you can now have your device actually owns the line. The line actually doesn't sit in the CPU cache somewhere, you own the line. And the CPU is actually snooping you, saying, hey, do you have an update to the line? Do you have an update to the line? So really cool, a lot of really cool use cases you can build around this, but it's also very, very complicated, right? Now you are participating in a cache coherency paradigm that has been typically behind a closed off wall. And if you screw it up, some very bad things happen. Also, the CXL protocol itself has oversight by the CXL consortium. Srijit sort of mentioned that. They're very, very similar to the PCI SIG that manages the PCI Express specs. So the CXL consortium is a multi-vendor, no one vendor is kind of in charge of it, although the CXL specs look eerily familiar to font-wise of Intel specs. But it's made up of a number of different vendors. Jump is actually a member of the CXL consortium. I'm one of the voting members on behalf of us. And Alejandro actually also alluded to this, but it is the last interconnect standing. So when I started working on CXL about 3 years ago, there were 2 other interconnects that were sort of trying to do the same thing. So CCIX or C6 was primarily driven by AMD originally. It actually is in some AMD silicon. It's also in Ampere silicon, I believe. So it's a very similar protocol or a set of protocols. And then Gen Z was one that was primarily driven by HP and was sort of similarly doing the same things, but was much more of the fabric stuff that Srijit was talking about with CXL 3.0. So CCIX kind of died. People just got less interested in it and hopped on the CXL bandwagon. And then Gen Z actually got eaten by CXL. Last year, all of the IP transferred over, and lo and behold, all of the fabric management and RAS that was in Gen Z showed up in CXL 3.0. Okay, so this is where reality kind of hits you in the face, right? So Srijit kind of talked about the different versions of the CXL specification. So CXL 1.1 was June of 2019. There was a 1.0, which was in March of 2019, quickly followed on with some minor edits. 2.0 is 2020, 3.0 2022, and then CXL 3.1, we just finished ratifying that a couple months ago. Has to go through a baking period and making sure that anyone wants to scream about wording of something. That should release by next month. Okay, so specifications have been around for quite some time. But you can't plug in a spec, right? So, Intel Sapphire Rapids launched January of this year, and Genoa was late last year. Emerald Rapids will likely, Intel said it should launch December 13th of this year. AMD Turin is the next generation beyond Genoa, should be late next year. And Granite Rapids should also be late next year. Why are these significant? Because these 3 CPUs at the top, the Sapphire Rapids, Emerald Rapids, and Genoa, all launched with CXL 1.1 support. So all of those cool whiz-bang features in CXL 2.0 and 3.0 and 3.1 that look really cool on the CXL consortium slides aren't in what we have today, aren't even close. And like Srijit also alluded to, it's CXL 1.1-ish. Depending on which CPU vendor you actually work with, depends on what the definition of the ish is. And so that's mildly frustrating. It's like the beauty of a spec is you have so many to choose from and how to actually implement them. So CXL 2.0 is what's targeted for these things late next year, right? So that's kind of out of sync with the spec timeline. And 3.0, who the hell knows? So 3.0, I mentioned it's not an extension of PCI Express. However, it does require the hardware on the PCI Express side, the physical interconnects. So CXL 3.0 is actually requiring PCI Express 6 and the interconnect changes that are there. The PCIe 6 spec is out. CXL 3.0 spec came out shortly after that. So whenever the next gen beyond Granite Rapids or the next gen beyond Turin is and they pull in PCI Express 6, that's when we'll likely see CXL 3.0 and all of the wonderful things that Srijit was talking about, this fabric and all the RAS features. Okay, so how does this map to what's actually upstream in the kernel? The nice thing is we actually have fairly robust upstream support for CXL. There's a lot of CXL code. It's like, go and read the comments, and there's like, hey, spec 3.0 section, blah, blah, blah. Well, the spec version 3.0 should be kind of a red flag to you. And I did include a link. It's actually kind of hard to see on the screen, but if you grab the slides later, there's a whole CXL drivers thing upstream. Dan Williams at Intel is one of the maintainers, has done a really nice job of shepherding this along. But the thing is, on the for the upstream, the support around this is really around mostly around memory type 3 memory expanders. So if we think back to Srijit's talk about an hour ago. The Type 3 devices are these I/O and MEM devices, and they're intended to be a memory expansion thing. So in reality today, if you wanted to actually Google Type 3 devices, or Bing, or whatever your DuckDuckGo is your thing, the Type 3 devices that you will actually find today on the market are, a lot of them are from Samsung. So this is a method of saying I want a shelf, like a disk shelf, something I stick in a rack, and instead of having disks and stuff in it, I have a bunch of DIMMs. Then I've got a CXL controller on the back that knows how to talk Type 3, which is .io and .mem. The type things are all marketing crap, so, but you have to kind of talk about it because that's how they call it out in BIOSes. And that plugs into a host and into a CXL controller, and then poof, you have expanded memory. So this was also very attractive to Meta. I'm trying to remember, I was trying to remember this morning when I was finishing these up, if it was early this year or late last year, Meta publicly announced their intent to introduce this pooled tiering for memory expansion for basically to support CXL, so that there would be ways that you can take your disk shelves, and in Srijit's one slide with all the different latency numbers, they were actually trying to map some of that to kernel memory enumeration, so that you have your NUMA nodes, which you have a distance to them, you have CXL attached DDR, which is kind of a NUMA node today, but what is it? Like how far away actually is it? So they're trying to make some changes upstream to realize that, which is kind of cool. So the upstream code also presents standard memory device files. So like a /dev character device file pops open, very similar to dev-mem that you can open up and do all sorts of things with. There's a whole set of really nice user space tools as well. If you actually look at the link, if you could actually read it on the screen, NDCTL was actually for the NVDIMMs. So the 3D Crosspoint tech that was supposed to be like the end-all be-all to next-gen memory stuff. A lot of this framework for the CXL memory stuff is actually built on top of that, and there's no coincidence because Dan also worked on the NVDIMM stuff. But there's a really nice set of tools, a nice set of man pages. They actually work, sort of. So the unfortunate realities. The upstream is chasing the latest spec, right? So there is CXL emulation support in QEMU. So if you wanted to go grab latest version of QEMU, you can probably fire up a CXL 3.0 root complex, or it's not really a root complex, but you have a CXL 3.0 environment, and then good luck trying to find a CXL device to plug into it. But this really does present some issues, right? So this is where we have some mismatches between what is real and what is slideware, right? So I have this link here off to a commit upstream that I'm going to just show the picture on that so it doesn't render wrong. Yeah, there it is. So this is, let me find my mouse pointer here. So this is from Dan. This is a patch from late last year, trying to, like, don't worry about the terminology here, but the thing to really kind of look at is that the root of all of these hierarchies for the memory devices started this ACPI 0017 table. This is something that the system BIOS and the CPU should be exporting as part of the firmware initialization before the kernel boots, as part of the ACPI handoff. And all of these things, like these D ports, are part of the CXL hierarchy, and then the endpoint would be like your .mem device. So it starts at this ACPI 0017 table, which is fine. So hold on to your pants here. Oops, no, that's not what I want. Gosh darn it. Technical difficulties. Here we go. Okay, so here we have, this is a Sapphire Rapid, so get out your little magic decoder rings and look up what the 8462Y plus Xeon Platinum is. It's a Sapphire Rapids, just trust me, trust me. And if you go and look in Sysbus ACPI devices and look in the ACPI tables that are actually exported, you get down to ACPI 0016, and there is no ACPI 0017, and you're like, what the fuck? I lost weeks of my life over this one. So this is actually the root of how to support type 3 devices, is that you need this table to then build the hierarchy to actually have a dev-mem device instantiated. So if you look really close at the launch marketing for Sapphire Rapids, it says, hey, we don't support type 3 devices. We support type 2 devices. But you can make a type 2 device look like a type 3 device. So this is part of the reality that you can deal with, is there's a BIOS entry in Sapphire Rapids BIOSes that says support legacy support for type 3 devices. And I'm like, it's a brand new protocol. Why do we have something called legacy? Anyways, you can tell that I'm a little bit passionate about some of these things. Genoa, if you look at AMD's Genoa, it says, hey, we support type 3 devices. We don't support type 2 devices. This is part of the 1.1-ish thing. But on Genoa, they actually do support .mem, type 3 properly. They do have this ACPI table. And we also got our hands on some Emerald Rapids, and lo and behold, this ACPI table magically showed up, and now Emerald Rapids supports type 3 devices. That's part of my life I'll never get back, but that's okay. Okay, but it's not all bad, and it's not all ugly. There actually are some successes with CXL with the current generation of hardware. It's just dependent on like how hard do you want to work for it. So here, I've scrubbed a lot of the information around this to protect the innocent. But from a dmessage boot log, this is with a CXL device sitting in a host. Can't tell you what it is, but just trust me, it's a CXL device. And it is a type 2 device with memory, right? So this is actually how it would show up. So the system BIOS goes ahead, goes out and maps it all, says, hey, I found like a mem region on a device, and I'm gonna map it into your physical address map. So you can look and see like, okay, this is a 2-socket system, 2 NUMA nodes. I've got node 0 is mapped to these physical addresses. Node 1 is mapped here, and then node 2. So this like weird node 2 is this, and if you did the math, this is 1 gig of RAM. And that would match with other support that we have in LSPCI that can actually decode some of the CXL, what we call the DVSec headers, or the designated vendor-specific headers. So this would be down part of the bottom of the LSPCI dump. And you can see that there's CXL capabilities, CXL control. So what is the device actually saying it's capable to do, and then what did it actually train? Right, so the cache IO mem, again, these are all 3 different protocols, and they all train differently in the link training sequence on the hardware. So you could be capable of cache IO mem, but plug into a system that doesn't support type 2, and you're gonna just train up IO and mem. Okay. Are there any questions about this so far? Have I put everyone to sleep yet?
What are the 3 rows? Cap, CTL, and STA?
Okay, so in the PCI, I should have put more of the LSPCI dump in. I just couldn't fit it on the slide. So the first line is CXL capabilities. So this is very similar to PCI capabilities as well in like other blocks. So typically you'll have a device that advertises what it's capable of. Like, is it capable of Gen 5 by 16? And then when it trains, then it actually says what is the control, which is the status, which is a terrible naming. But the control is the actual active state. So this says, yes, cache plus, IO plus, mem plus means all 3 actually linked up. And then the status, this is the viral thing. So this is, the funny thing is that if this ever went plus, your system is about to machine check. So it's like, I don't even know why we even report the viral bit. Something very bad happened on the bus. Like malformed flit, you set an opcode that was incorrect. Something that pissed off the IOC is what will actually trip viral. But yeah, like I said, it's a canary that will never get heard because usually there's a panic on its way. Okay, any other quick questions? I know we're butting up against the time here. I'll try to zip it forward. Okay, so continued realities. So, okay, I got this node 2 that showed up. I actually don't have a NUMA node that shows up. I can if I want to, but I have to be able to officially support a type 3 device for that to happen. So, yeah, and if you also try to bring it online as a NUMA node, so it shows up in sys, devices, platform, node, whatever, Then the CPU happily starts trying to send random memory reads and writes to initialize memory, and if your device isn't ready for that, it'll really piss it off, and it'll trip that viral bit. So there's a different way that you can actually specify memory, and this is part of the CXL spec. You can tell it, I want this memory to be basically reserved. I want this EFI special purpose memory. That's how the BIOS maps it. That's how it shows up in the OS, and the OS says, I see physical memory, but I know I'm not supposed to do anything with it. So that's actually perfect for a driver to come along and allows us to map it. So you basically have to then go do what all of the upstream code does today, but it can't because there's no ACPI table. You parse out the DVSec headers and look at the registers to basically find where is my memory, where did it get mapped. So very similar to bar discovery with the PCI, PCI find resources, select bars, something that probably a lot of us can do in our sleep. You actually have to do this open-coded right now with CXL. Depending on how your device is configured, there's also these things called HDM, or Host Managed Device Memory Decoders. This says, where is your .mem memory? And that will be written to by the BIOS to say, this is where I mapped. So it's basically, again, it's almost the same thing like a bar. And then you can IRE map it. So you can IRE map it, like Srijit was saying, like now you have different ways that you can actually handle this memory. You can do write back, you can do write combining, you can do uncached, all sorts of things. And then I threw this in that you might also have to have a knife fight with config DAX HMEM. This is something that was enabled by default many kernel versions ago that says, hey, there's memory here, let me bring it online. And we'll actually IRE map it for you to something that you probably don't want. So when your driver comes along and tries to IRE map it, then it throws a very cryptic message and you scratch your head for a long time. So, so theoretically, you'll have to do this. I lost many hours again debugging this, so just keep that in your back pocket. Okay, so kind of reiterating what Srijit said, I think CXL 2.0, I really believe that that's going to be where things kind of converge. CPU vendors, I think, are going to be able to figure out what they have to do, get it clean, get the interfaces correct, be really true to the spec. We can actually start leveraging a lot of the upstream stuff. CXL 2.0 is also where hotplug shows up. So in shops that use FPGAs a lot, when you reprogram FPGAs, depending on how you actually have the chip layout, you may have to basically reboot the FPGA. Like if you overwrite the PCIe block or the CXL IP, then you have to kind of like reboot the card so it can retrain, right? So in CXL 1.1, there is no hot plug, which is very challenging for anyone. I actually brought this up at the CXL micro conference at Plumbers last year, and everyone's like, what? Like, how did we miss that? Like, we've been screaming about it for like 3 years now in the consortium, but anyway, so 2.0 is where that shows up. The standard tools that are out there, we can actually start using them on CXL 2.0 and CPUs that support it, which will be really, really nice. And then in CXL 3.0, in addition to all of the fabric and mesh stuff that Srijit talked about, it also has a lot of the reliability stuff with like healing and error detection and all sorts of stuff that was all in Gen Z that got consumed by CXL. Okay, that's it.
So since Jamal consumed all the questions time, I'm kidding. We maybe have time for 2 questions if people still have them.
I just wanted to say, no wonder they didn't want to do hot plug. If everything looks like memory, hot plug memory was really hard.
So the statement, and it's very true, is that hot plug, I'll summarize, hot plug is very hard, right? Because if your device is actually showing up as host memory, then you're dealing with the memory hot plug subsystem. And it actually gets even worse because if you're a cache coherent peer, then you're also doing effectively CPU hot plug.
Actually, it's even worse because the hot plug you're thinking of is non-interleaved. CXL memory can show up as interleaved, right? It's just a...
Yeah, that's good, very good point. Doesn't mean that I don't want it right now, but
If you guys can use the mic is there a mic on that side? We have 2.
I don't think that...
Tom,
are there any questions?
Oh, Tom has it, okay. Tom, you're hogging the mic, man.
There are no questions. I think everybody's ready for a break. Thank you.
Yep, thank you.